Somewhere in the southern Indian Ocean, a Boeing 777 may still be lying on the seafloor. It is not a small object. Its wings stretch more than 60 meters across. And yet, after more than 12 years, nobody can point to the wreckage. That is not because we lack technology. Modern sonar can map the deep ocean in remarkable detail. Autonomous robots can descend almost 6 kilometers and search for hours without a cable connecting them to the surface. The real problem is harder. We may still not know exactly where those robots need to look. Since Malaysia Airlines Flight 370 disappeared, search teams have followed satellite signals, tracked drifting debris, mapped unknown parts of the seafloor, and sent sonar-equipped robots into the deep. They have found geological formations. They have found old shipwrecks. They have investigated unusual sonar contacts. But they have not found MH370. And even now, the search is not finished. A new campaign began in 2025. Thousands of square kilometers were surveyed. Nothing confirmed the aircraft's location. Then Malaysia extended the search agreement into 2027, leaving thousands of square kilometers still to be completed. So this is not just a 12-year-old mystery. It is an active deep ocean search happening right now. And the strange thing is that, in some ways, we know far more about MH370 than we did when it vanished. We know the aircraft kept flying after normal contact was lost. We know it communicated with a satellite for hours. We know parts of it eventually reached shores in the western Indian Ocean. We know where previous search teams looked. We even know where some of the weaknesses in those old searches may have been. What we still do not know is the one thing that matters most: where the aircraft finally came down. And to understand why that question is still open, we have to go back to the night MH370 disappeared. Because the aircraft vanished from radar. But it did not vanish from everything. Malaysia Airlines Flight 370 left Kuala Lumpur shortly after midnight on March 8, 2014. Its destination was Beijing. There were 239 people on board. For the first part of the flight, everything appeared routine. Then the aircraft stopped behaving like a normal commercial flight. Its transponder was no longer giving civilian controllers the information they expected. The aircraft did not continue northeast toward China. Instead, radar evidence later showed that it turned back across the Malaysian peninsula. Military radar tracked it moving west, then northwest. And eventually, it went beyond the useful range of that radar too. At that point, the problem became much bigger than a missing radar target. Nobody knew where the aircraft had gone next. And that uncertainty shaped the early search. Aircraft and ships were sent into areas that later evidence would make much less likely. Every hour that passed allowed the possible search area to grow. But investigators were about to discover something unexpected. MH370 had left behind another trail. Not on radar. In space, the Boeing 777 carried satellite communication equipment. And although there was no meaningful conversation coming from the aircraft, the system continued exchanging automated signals with an Inmarsat satellite network. These were not position reports. They did not say, "The aircraft is here." They were more like digital check-ins. A machine asking whether another machine was still there. And MH370 kept answering. That changed everything. Because even though those signals had never been intended to track a missing airliner, engineers realized they contained information about distance and movement. The aircraft had not left investigators a map, but it had left them enough to begin building one. And that is where the story becomes less about aviation and more about physics. Here is the basic problem. Imagine you know that an object is exactly 1,000 kilometers away from you. That sounds useful, but you still do not know where it is. It could be north, south, east, west, or anywhere along a huge circle around your position. That was roughly the kind of problem investigators faced with the satellite signals from MH370. One part of the data was called burst timing offset, or BTO. Without going too deep into the engineering, BTO helped analysts estimate the distance between the aircraft and the satellite system at the moment a signal was exchanged. That immediately ruled out huge parts of the world. But it did not produce a dot on a map. It produced an arc. MH370 could have been somewhere along that arc. So investigators looked for more information inside the signal. That led them to burst frequency offset, or BFO. This measured small differences in frequency. Those differences could help analysts understand how the aircraft and satellite were moving relative to each other. You can think of it as a very complicated version of the Doppler effect. A car approaching you sounds different from the same car moving away. Radio signals shift too. But in this case, the calculation was much harder. The satellite was moving. The aircraft was moving. The Earth was rotating. The electronics inside the aircraft's satellite system had their own behavior. And investigators did not know the aircraft's exact speed or heading. So they tested possible flight paths. Some fit the recorded signals better. Others did not. Little by little, the possibilities narrowed. And one broad conclusion became increasingly difficult to avoid. After disappearing from normal tracking, MH370 had likely continued flying for hours. And it had likely gone south into the Indian Ocean. That was a remarkable breakthrough. But it created a new problem. The final satellite exchange occurred around 00:19 UTC. From that exchange came what is now called the seventh arc. You have probably seen it on maps of MH370. A long curved line across the southern Indian Ocean. But the seventh arc is not a crash line. It does not say the aircraft hit the water exactly here. It represents possible positions associated with that final satellite communication. That distinction matters, because once investigators began asking where along that arc the aircraft might have ended its flight, every assumption changed the answer. How fast was it flying? What heading was it on? When did fuel exhaustion occur? What happened after the engine stopped? How steeply did the aircraft descend? Was the autopilot still controlling anything? Was there any manual input near the end? You can model those questions, but you cannot remove all uncertainty from them. And this is where the scale of the problem starts to become clear. On a world map, the seventh arc looks narrow. On the ocean, it is enormous. Move your assumed endpoint a little north or south, and you are no longer talking about a small correction. You can add thousands of square kilometers to the search. The satellite data had done something extraordinary. It had turned a missing aircraft into a much smaller problem. Just not a small problem. And now the search was heading toward one of the most remote parts of the planet. The southern Indian Ocean is the kind of place where distance changes everything. There are no nearby cities, no chain of airports, no easy way to replace damaged equipment. A search vessel may spend days simply reaching the area where work can begin. That means every hour at sea has a cost. Weather can stop useful work. Equipment failures can cost an entire day. And if a sonar system is being towed deep below the surface, even ordinary movement at the ship has to be managed through kilometers of water and cable. Autonomous underwater vehicles reduce some of those problems, but they still have to be launched, recovered, prepared, and their data reviewed. So yes, depth is a problem. But before depth, there is another one. Scale. A Boeing 777 looks enormous at an airport. Put one beside a terminal, and it dominates the scene. Put the same aircraft in the southern Indian Ocean, and it becomes tiny. Now add uncertainty. If your estimate of the final position is off by 20 or 30 kilometers, You do not just move one search line. You may have to move an entire search corridor. And because the seventh arc is so long, small changes in the assumptions can produce huge changes in the area that needs to be covered. This is why people sometimes misunderstand the size of the MH370 search. Investigators were not searching such a large area because they had no idea where the aircraft went. They were searching a large area because the evidence pointed to a region, not a point. And even after they had a region, another problem appeared. They did not have a detailed enough map of the bottom. That sounds strange. We have satellites that can map continents from space. We have photographed other planets. Surely the floor of the Indian Ocean was already known. At a broad scale, yes. At the level needed to safely fly sonar systems close to the seabed. Not nearly enough. So before teams could seriously search for MH370, they first had to map the landscape where they thought it might be. The deep ocean is not a flat, featureless plain. And the MH370 search area made that very clear. Survey ships used multi-beam sonar to build detailed maps of the seabed. A multi-beam system sends sound downward in a wide fan. Those sound pulses hit the bottom and return. Measure the travel time, and you can estimate depth. Do that across thousands of lines, and a three-dimensional landscape begins to appear. What search teams found was complicated terrain. Ridges, underwater mountains, deep depressions, fracture zones, steep slopes. One of the major features in the region is Broken Ridge, a huge geological structure on the ocean floor. In other areas, the terrain rises and falls by hundreds of meters. And the water above it can be several kilometers deep. That changes how you search. A sonar vehicle needs to stay within a useful distance of the seabed. Too high, and the image becomes less useful. Too low, and you risk flying the vehicle into the terrain. For a towfish connected to a ship by kilometers of cable, controlling that height is not simple. The ship may be in calm water at the surface, while the seafloor below suddenly climbs toward the sonar system. An autonomous vehicle can follow the terrain more intelligently, but it still needs good maps and careful mission planning. A simple way to picture this is to imagine searching for a crashed aircraft somewhere in a mountain range. Now turn off every light. Flood the mountains. Move yourself 5 kilometers above them. And try to find the wreckage using sound. That is much closer to what the teams were dealing with. So the bathymetric survey was not something separate from the MH370 search. It was part of it. Before crews could search the bottom in detail, they had to understand the bottom well enough to work there. And that work had an unexpected benefit. The search produced some of the best maps ever made of parts of this remote section of the Indian Ocean. But those maps still did not answer the main question. They showed the shape of the landscape. They did not show MH370. For that, teams needed higher resolution sonar. And this is where another misunderstanding begins. Because sonar does not show you the seabed the way a camera does. If you imagine an underwater search vehicle moving through the dark with a camera pointed at the bottom, that is not completely wrong. But cameras are usually not how you search a huge area first. At several kilometers of depth, a camera sees only a small patch of seabed at a time. Sonar can cover much more ground. It sends out sound and listens for the echoes. Hard surfaces may reflect strongly. Objects can cast acoustic shadows. Different shapes produce different patterns. That gives analysts an image of sorts, but it is not a photograph. They are not waiting for the outline of a Boeing 777 to suddenly appear on the screen. They are looking for things that do not belong. A cluster, a strange shape, several strong reflections close together, a shadow that suggests an object rising above the bottom, something that looks artificial rather than geological. Those are called contacts, and there can be a lot of them. During earlier searches, analysts identified hundreds of lower-interest contacts. More than 20 were interesting enough to receive a higher classification. Only a tiny number reached the highest priority. Now imagine being on the team when that happens. You have spent weeks looking at almost nothing but seabed. Then an object appears. The return looks wrong. Too regular, too hard, too different from the surrounding geology. So the team goes back. A sonar vehicle flies closer this time. The image improves. And if the target still looks promising, a camera may be sent only a few meters above the bottom. This is the moment people imagine ending the mystery. The camera approaches. The lights come on. And then, rocks, or the remains of an old ship. That actually happened. One high-interest contact proved to be a rock field. Another turned out to be a shipwreck. And that tells us something important about what a real MH370 detection may look like. Search teams are probably not looking for an intact Boeing sitting neatly on the seabed. The aircraft may have broken apart during impact. Large structures could be separated. Smaller pieces could be spread over a long debris field. Some parts may be obvious. Others may blend into the terrain. So the target may not look like an airplane. It may look like a pattern that nature would be unlikely to create. That is what experienced sonar analysts are trying to recognize. And modern sonar is very good at this. If the sensor passes close enough. That last part is the problem. A sonar system can only image the ground inside its swath. It cannot see wreckage 10 kilometers outside the line being searched. It cannot compensate for a crash model that put the search area in the wrong place. And this is going to matter much more later. But before search teams understood that problem fully, something else happened. A real piece of MH370 came back. Not from the seafloor, from a beach thousands of kilometers away. For more than a year after MH370 disappeared, investigators did not have a confirmed piece of the aircraft. They had models, radar, satellite signals, search maps, but nothing physical from the airplane itself. Then in July 2015, something washed ashore on Reunion Island. It was part of an aircraft wing, a flaperon, and investigators confirmed that it came from MH370. For the first time since the disappearance, the missing aircraft had physically reappeared. Only a piece of it. But that piece changed the investigation. More debris would later be found around the western Indian Ocean and along the East African coast. Some pieces were confirmed as coming from MH370. Others were judged highly likely or possible. Together, they supported something the satellite data had already suggested. The aircraft had ended up in the Indian Ocean. That sounds like a major breakthrough. And it was, but not in the way people might expect. Because the ocean had moved the evidence. A floating piece of wreckage does not stay above the place where an aircraft entered the water. Currents carry it. Wind pushes it. Waves change its motion. Large ocean systems shift with seasons. A piece of debris can travel thousands of kilometers before anyone sees it again. So finding the flaperon did not tell investigators where MH370 crashed. It gave them a new question. If this object arrived on Reunion at this time, where could it have started? Researchers at Australia's CSIRO tried to answer that with drift modeling. They used ocean current data, winds, drifting buoys, and eventually, they tested how a real Boeing 777 flaperon behaved in the water. The idea was simple. Start simulated debris at different points along the possible crash region. Let the model carry it through the Indian Ocean. Then compare the results with where real wreckage had actually been found. Some starting areas made more sense than others. That helped shift attention toward particular parts of the seventh arc, including areas farther north than the earliest underwater search priorities. And now something interesting was happening. The satellite evidence had been created in space. The debris evidence had been carried across the ocean. Two completely different systems were beginning to point toward overlapping parts of the same broad region. That increased confidence, but it still did not give anyone a crash coordinate. The debris had confirmed the Indian Ocean. It had not told searchers exactly where to send the next sonar line. And by then, those sonar lines were covering an enormous amount of ground. The first major underwater campaign eventually covered around 120,000 square kilometers of high-priority seabed. Think about that for a moment. That is not a quick sweep across a small accident site. It is a full industrial operation carried out in one of the most remote oceans on Earth. Search ships worked line after line. Sonar data came in. Analysts reviewed contacts. Weather stopped operations. Equipment was repaired. Areas were rescanned. Months passed, then years. By January 2017, the search had been running for 1,046 days since the aircraft disappeared. An MH370 had not been found. That was a devastating result. But it did not mean the search had learned nothing. A good negative result still tells you something. If an area is searched with enough confidence and there is no wreckage, that area becomes less likely. You can move the next search somewhere else. So experts went back to the evidence. Satellite data, aircraft performance, possible end-of-flight behavior, debris drift, previous sonar coverage. In late 2016, a first principles review identified an additional area farther north along the seventh arc as especially important. But the original search ended before every part of that proposed region could be examined. Then Ocean Infinity entered the search in 2018 with multiple autonomous underwater vehicles, allowing several strips of seabed to be covered in parallel. The technology was faster, the coverage expanded, and still no MH370. By then, huge areas had been mapped or searched, and the aircraft was still missing. So maybe the seventh arc was wrong. Maybe the search had focused on the wrong part of the ocean. Or maybe the problem was hidden inside a word everyone kept using. Searched. Because in deep ocean work, that word is not as simple as it sounds. Suppose someone tells you a city has been photographed. That does not tell you much. Was the image taken from a helicopter? Can you see individual cars? Or was it taken from a satellite so far away that an entire block is only a few pixels wide? Both images cover the same city. Only one may be useful if you are looking for a specific vehicle. The same idea applies to sonar. Two parts of the ocean can both be marked as surveyed, but the quality of the data may be very different. Some sections of the MH370 search were covered with high-resolution sonar from vehicles operating relatively close to the seabed. Other areas were mapped mainly to understand the terrain. Some had overlapping search lines. Others had gaps. Surveyors sometimes call those gaps holidays. It means part of the planned coverage was missed. That can happen for ordinary reasons. Terrain changes. Sensors move. Lines do not overlap perfectly. The outer edge of a sonar swath may be weaker than the center. The vehicle may have to change course. None of that means a search was badly run. It means real-world search data is messy. And that matters when the object you are looking for may occupy only a small part of a huge seabed. In 2022, Australian authorities asked Geoscience Australia to review sonar imagery from part of the old MH370 search after an independent researcher proposed a new location. The review did not confirm that proposed theory. In fact, within the high-quality area they examined, Experts considered an MH370 debris field very unlikely. But the review exposed something more useful. Old sonar data still contained things worth checking again. Analysts identified 11 contacts that had not been fully analyzed during the original search. After review, none looked like an aircraft debris field. Some appeared geological. A few may have been human-made objects. But the important lesson was not that MH370 had secretly been hiding in old data. It was that search confidence depends on more than whether a ship passed through an area. You have to ask what data was collected. At what resolution? How close was the sensor to the bottom? Was the entire area covered? Were there gaps? Was the terrain difficult? Was the data reviewed again after better processing became available? This is where the phrase, "they already searched there," starts to fall apart. Because a low-resolution bathymetric survey and a high-resolution sonar pass do not answer the same question. One may tell you that a ridge is there. The other may help you decide whether a debris field is lying beside it. That difference changes the whole MH370 search. For years, the public question has often been, how could sonar miss a Boeing 777? But that may be the wrong question. Modern sonar probably does not need to miss the wreckage at all. It only needs to never pass close enough to see it. And that is a completely different problem. Now the search becomes less about whether the technology works and more about where you send it. Which strip of the seventh arc deserves another look? Which previous areas are genuinely cleared? Which parts were only mapped at lower resolution? Where were the gaps? And which assumptions about the final flight are strong enough to justify spending millions of dollars searching another box of ocean? This is the point where the MH370 mystery becomes a probability problem, not just a technology problem. And the strange part is that the technology itself has become much better. Ocean Infinity's modern search systems are far more capable than the tools available when MH370 first disappeared. But better robots solve only one part of the problem. They make a search box easier to search. They do not decide where the box should be. Autonomous underwater vehicles can descend thousands of meters, work without a physical cable to the ship, and carry high-resolution sonar close to rough terrain. Several can operate at the same time, covering different corridors in parallel. That is exactly the kind of technology people imagine should finally solve MH370. And maybe it will, but only if the search box is close enough to the real crash site. That still comes from the evidence. Satellite analysis, fuel estimates, aircraft performance, drift models, previous search results, end-of-flight simulations, and judgments about which old areas can be eliminated with enough confidence. The AUV does not know why it is searching a particular strip of ocean. It simply follows the plan. So imagine a modern robot covering the seabed with excellent sonar. The data is sharp. The navigation is accurate. The mission runs perfectly. If the wreckage is 20 kilometers outside that corridor, none of that matters. The robot did its job. The search model was just not close enough. This is why unsuccessful searches are not completely useless. Every well-covered area where MH370 is not found removes another place from the map. It is slow progress, but it is progress. Ocean Infinity says that across its MH370 efforts since 2018, it has spent more than 150 days at sea and mapped more than 140,000 square kilometers of seabed. And by 2025 and 2026, its robotics, automation, and operational experience were much more mature than during the first search. Yet the aircraft was still not found. That tells us something. The deep ocean technology may no longer be the weakest link. The uncertainty in the crash location may be. And that is exactly why the newest search matters. because it is trying to take more than a decade of evidence and compress the problem into a smaller area. In March 2025, Malaysia formalized a new agreement with Ocean Infinity. The new search area covered roughly 15,000 square kilometers of the southern Indian Ocean. The arrangement was based on a no-find, no-fee model. If qualifying wreckage was found, Ocean Infinity would receive a $70 million success payment. If it was not found, Malaysia would not pay that fee. That structure makes sense only if the company believes the search area is worth taking seriously. Operations took place in 2025 and resumed around the end of that year into January 2026. Across the formal search phases after the agreement, about 7,571 square kilometers were surveyed. Sea conditions and weather interrupted some operations. No confirmed wreckage was found. On January 23, 2026, the vessel left the area. That could easily have been the end of the story. It was not. In June 2026, Malaysia announced that the agreement would be extended for another year, through June 30, 2027. Around 7,428 square kilometers of the defined search area remained. In other words, roughly half of the new search box was still unfinished. That is why the story is still active now. And the new search is not simply repeating what teams did 12 years ago. The target area is much smaller than the huge regions once under consideration. The technology is better. Search teams have years of previous sonar results to work from. Debris drift has been studied in more detail. The satellite analysis has been revisited again and again. And each old area searched without success removes more possibilities. That should make the new campaign more promising. But it should not make us overconfident, because every search box is built from assumptions. Good assumptions, evidence-based assumptions, but still assumptions. The seventh arc is not a crash coordinate. Drift modeling does not run backward like GPS. Fuel modeling depends on aircraft behavior. The final satellite signals still require interpretation. Even the last moments of the flight are not known with certainty. So here is the situation in the simplest terms. If MH370 lies inside the remaining search area, modern sonar and AUVs have a real chance of finding it. A debris field from a Boeing 777 should produce patterns that experienced analysts can investigate. Suspicious targets can be rescanned. Cameras can be sent down. And one good sonar line could end a 12-year search. But if the true crash site lies outside the box, the same technology could perform perfectly and find nothing. That is the uncomfortable part. A search can be technically flawless and still be looking in the wrong place. And that is why the next phase matters so much. Not because anyone can promise MH370 is there, but because if it is there, the tools available today may finally be good enough to prove it. Then another question begins. What would finding the wreckage actually tell us? Imagine one of the AUVs finishes a mission. It comes back to the surface. The data is downloaded. An analyst starts reviewing the sonar. Most of the screen looks familiar. Sediment, ridges, natural shapes. Then something appears that does not fit. Several hard objects, strong returns, regular geometry, a pattern spread across the bottom. The team marks the location. A second survey is planned. This time the sonar flies closer. The target becomes clearer. Then a camera goes down. And after more than 12 years, the main wreckage of MH370 is finally visible on the seabed. What happens next? The first thing investigators gain is the most basic thing they have never had. A location. The exact crash site could be compared with years of satellite modeling, fuel analysis, drift studies, and end-of-flight simulations. Some search theories would look much stronger. Others could finally be rejected. The debris field itself could also tell investigators a lot. How widely was the wreckage spread? Which major structures remain together? Where are the engines? The landing gear? Large sections of fuselage? Control surfaces? The condition and distribution of those parts could help investigators understand how the aircraft entered the ocean. Then there are the recorders. The cockpit voice recorder and the flight data recorder. Both were designed to survive severe accidents, but they were not designed with the expectation that they might sit for more than a decade under several kilometers of seawater. Their locator beacons stopped transmitting years ago. Their physical condition is unknown, and even if they were recovered, nobody can guarantee usable data would remain. There is another limitation people often overlook. Finding MH370 would not automatically explain why MH370 disappeared. Those are two different questions. The official Malaysian investigation did not determine why the aircraft diverted from its planned route. Evidence suggested that the early change in flight path likely involved manual inputs. But that does not tell us who made them. It does not tell us why. It does not tell us what was happening in the cockpit. Investigators did not find a technical failure that convincingly explained the entire sequence. But without the main wreckage and recorders, some technical possibilities could not be completely ruled out. Third-party intervention could not be completely ruled out either. And this is where discussion of MH370 often becomes messy. Over the years, that uncertainty has produced countless theories. But uncertainty is not evidence for any one of them. Finding the wreckage may shrink that uncertainty. It may eliminate some ideas. It may support others. But it is possible that even the wreckage will not preserve every answer. What it almost certainly would do is give the investigation something it has never had. A real endpoint. Right now, we know the aircraft did not continue normally to Beijing. We know it changed course. We know it remained airborne for hours after normal contact was lost. Satellite evidence strongly supports a flight south into the Indian Ocean. Confirmed debris from MH370 later reached distant shores. Fuel exhaustion is considered a strong explanation for the final phase of the flight. And the seventh arc remains central to the search. But the exact crash location is still unknown. And without that location, every other question becomes harder. That matters scientifically. It matters for aviation safety. And for the families of the 239 people on board, it matters in a much more personal way. For them, MH370 is not just an unsolved engineering problem. It is an event that never received a physical ending. There is no known crash site, no main wreckage, no place that finally answers the simplest question. Where did the flight end? That is why finding the aircraft still matters, even if it does not solve every mystery around it. Because one answer may still be waiting on the bottom of the Indian Ocean. From the surface, the southern Indian Ocean gives almost nothing away. A search vessel can travel for days and see the same thing in every direction. Water, clouds, waves. There is no marker showing the seventh arc. No sign above the place where the aircraft may have entered the ocean. But thousands of meters below, the landscape is anything but empty. Ridges rise from the seabed. Fracture zones cut through the terrain. Sediment covers old geological structures. Shipwrecks from other eras lie in the dark. And somewhere among all of that, MH370 may still be there. An autonomous vehicle moves above the bottom. Its sonar sweeps across another strip of seabed. Most of what it records will be ordinary. That is what searching looks like. Hours of normal terrain. Kilometers of nothing unusual. Then another line. And another. because the search does not need to find something everywhere. It only needs to cross the right place once. Over the past 12 years, each new piece of evidence has made the possible ocean smaller. Radar narrowed it. Satellite data narrowed it. Fuel modeling narrowed it. Debris drift narrowed it. Previous sonar searches narrowed it. The new search is trying to narrow it again. Technology has made the ocean smaller. It just hasn't made it small enough yet.